Hey there, welcome back to 2241. And today we're going to go over some examples of cross-product problems. And so we're going to start off with number one here that says, given two vectors u and v, find their cross products. And that's cross products in both orders. Remember that they are not commutative, or the cross product is not commutative, so these should be different. All right, and so let's start by computing u cross v. If you remember the formula, that's great. I like to use the determinant formula, makes things very easy, so let's do that. I, j, and k, and then I write u as a row vector, 1, 3, 4, and v as a row vector down here, 2, 7, minus 5. And then I remember my formula says, all right, look at I, and then take the determinant of this minor down here. And we should get, actually, let's write this in I notation. So 3, skipping ahead, sorry. So 3, 4, 7 minus 5 times I hat. All right, and then minus, this is position 1, 2, row 1, column 2, and that sum is odd. 1 plus 2 is 3. So we get a negative there. And then we take the determinant of this minor, 1, 2, 4, and minus 5. Let's write that down. 1, 2, 4, minus 5, and j hat. And then similarly, we will get 1, 2, 7, 3, k hat right there. And then you just need to remember the formula for the determinant of a 2 by 2 matrix. And that is not too hard. In this case, we are going to go across 3 times minus 5 and 4 times 7 plus minus. A little hard to see, isn't it? I'll make that bigger. So now we have 3 times minus 5 is negative 15. And then we want to subtract off 7 times 4, which is 28. All right, minus 1 times negative 5 is negative 5, minus 4 times 2 is 8. Notice there are a lot of minus signs popping up. Be very careful about those when you're doing these problems. All right, 1 times 7 is 7. Subtract off 3 times 2 is 6. And we get k hat. All right, and last but not least, we go ahead and add these all up. And we get 43, I think, minus 43 I hat. This is going to be plus 5 and 8 is 13, j hat. And then 7 minus 6 is 1, k hat. So that's how we compute the cross product u cross v. All right, and now we need to do v cross u. But do we really need to do this whole thing again? We do not, because if you remember, there's a property that says v cross u is the same as minus u cross v, and we already did u cross v. So all I have to do is change all the signs in my last cross product, and I will have u cross v, or sorry, v cross u. And then we will be done with that problem. It's helpful to know those algebraic properties, saves you from doing all of this work all over the place. You only have to do it a few times. All right, moving on to problem number 2. It says, show that u cross u is equal to 0 for any vector u. All right, well, let's see what happens here. If I just write out the formula, we know that u cross u is equal to u1, u2, u3, I, j, k above that, and then u1, u2, u3 below that, and determinant. They're not very straight. Good enough. All right, and now we do our formula again. We've got U2, U2, U3, U3, I hat minus U1, U1, U3, U3, J hat plus U1, U2, U1, U2, K hat. And our 2 by 2 determinant tells us we have U2, U3 minus U3, U2, but this is just regular multiplication of scalars, and so that is equal to 0. And if we look at the rest of these determinants, they look the same, so we end up with the same things, 0j and 0k, so we get just the 0 vector out here. There's also a general rule going on here that whenever a matrix has 2 rows or 2 columns that are the exact same, no columns in this case, but it can't happen, we have the second and third rows the exact same, its determinant will end up being 0. So if you think of I, J, and K as just being numbers instead, we get out 0. And same over here, we have the same columns, the same rows again, and those end up being 0. So if your matrix has 2 rows or 2 columns that are the same, you get out 0. Moving on to number 3, we have another geometric property that they want us to show. Show that U cross V is perpendicular to both U and V for all vectors U and V. Okay, well, what do we need to do here? We need to check U cross V. Remember what it meant for something to be orthogonal? That when you dot those 2 vectors together, you get out 0. And this is the scalar 0, not the vector 0. All right, so we take these 2 things and dot them together and see what happens. Now, if you remember, there is another property of the cross product and the dot product that says, all right, well, I'm allowed to move these parentheses over here. It just means that I have to swap the dot product as well. So this is equal to U dot and then V cross U. The U's have not changed position. This U is still this U, and this U is still that U. But I've moved the parentheses over and swapped the operators. Okay, so, well, now what? Who cares? Well, what happens is I get U dot, and then we have minus U cross V. All right. And we then get that if we add this to the other side of the equation, we get, I need to write that differently, U cross V dot U plus U cross V dot U equals 0. Okay, well, that is just twice U cross V dot U equal 0, and I can cancel out the 2 to get exactly what I want, that U cross V dot U equals 0. Okay. And so that gives us our first one, that U cross V is orthogonal to U itself. This should be similar for v. Let's take a look at it. So we've got u cross v dot v equals, okay, well, I don't really want to do a ton of work again. So if I do this, now I have something that looks exactly like what I had before. So if I now swap the labels on u and v, so here I had uvu, now I've got vuv, I have the exact same type of thing, and I'll be able to rearrange this just a little bit. Another thing you can do is also swap the cross product, v cross u minus dot v, and then here we get v dot v cross u. Oh, I need a minus somewhere. Minus v cross u. Then I can take this v right here, move it over, and we've got v cross u dot v equal v. That's not quite what I want, is it? V dot v cross u, I think. Oh, yes, that is what I wanted. So that means that I can okay. I think I might have made a mistake there. So let's ignore this for a second and just pay attention to this part. We can rewrite this like this, and that makes the problem look exactly like this one. And so we can use the same logic. Say, all right, well, the same sort of ruling applies, and so we get the same result, which tells us, well, dot, 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 that u cross v dot v is equal to 0. And so it is orthogonal to both. All right, number 4. Find a vector orthogonal to the plane pi, that's a capital pi, containing the points p, q, and r. So these 3 points are coplanar, but we want a vector that is orthogonal to the plane, which means that it should be orthogonal to 2 vectors between these points. So if I draw these points out, P, Q, and R, well, I get a triangle, but what I'm really interested in here is the vectors. Come on. P, Q. So let's say that this is P, Q, R. And we want to find a vector that is orthogonal to those. Well, remember that the line between P and R makes a triangle here, and so that gives us a plane. If the blue lines are vectors, we can cross them and get a vector in that direction. So what we want really is, if this is U and this is V, we want U cross V. So this is an example of recognizing that a geometric problem involves the cross product, or can be solved using the cross product. So what we need to do first is find U and V. So the way I've drawn them, U is the vector pointing from Q to P, which means I need the point P minus the point Q. So we have 1 minus -2 and 4 minus 5, and 6 minus negative 1. All right, that gives us a vector 3, minus 1, and 7. Same for v, we'll use r as the tip. And we get 1, minus negative 2, negative 1, minus 5, and 1 minus negative 1. This gives us our vector v, which is going to be 3, comma, negative 6, comma, 2. And now all we do is use our cross product. So we've got u cross v equal 3 minus 1, 7, 2, 6, 3, that's minus 6, I, j, k up there. And we just write out our formula here. We've got, I'll start doing things a little quicker here. So negative 2 minus negative, so plus 42, I hat, minus, let's see, so 3 times 2 is 6, minus 21, 7 times 3, j hat, plus 3 times negative 6 is minus 18, minus negative 3, so plus 3, k hat. This gives us our final vector here. This is 40 I hat plus, so 6 minus 21 is negative 15, 15 j hat, and then minus 15 k hat. And if we want, we can scale this down a little bit and get a vector w that has smaller integer coordinates. So we've got divide by 5, or 8. And we get 8, 3, 3. And then those are all coprime, so we've got the vector 8, 3, minus 3, which is then orthogonal to the plane pi here. Okay. It's orthogonal to the vectors u and v. Okay. Notice that it's totally fine for me to just divide this by 5 here, because it only says find a vector orthogonal to the plane. It doesn't say find a vector of length 7 or whatever. It just says find at least one. It could have been negative of w. I just need to find one of them, and then I get to submit whichever one I want as the answer there. All right, so here, let's now find the area of the triangle delta, or sorry, triangle PQR, given that P, Q, and R are these points. Okay, they're the same points as the previous problem, but I want the area of this triangle. And so now I need to rely on some geometric formulas. If you remember correctly, the cross product is the area of a parallelogram spanned by u and v. And we have a formula for the norm that is just like the geometric formula for the dot product, only we put a sine theta instead. So if we do this, we've got, let's draw our parallelogram here. A little better than that. Okay. So say this is our parallelogram. We've got u and v right there and there. And we want the area of the triangle. So remember, here's P, here's Q, and here's R. The area of this triangle right here. So A equals, now what is A? Well, the area of this whole parallelogram is this, the norm of the cross product. And this triangle is half of that. So the area here is half of the cross product norm U and V. All right, well, we found U cross V up there. We can find the norm of that directly. Or we can use this formula. Let's do both. So we'll use the formula first, which means that I need to find U norm and V norm. All right, so referencing back, my vector U was 3, -1, 7, which means my norm is 9 plus 1 plus 49. And my norm of V is square root of 9 plus 36 plus 4. All right, so that is 59, which is prime, and all 49. So square root of 49 is 7. So these are our two norms, and we get that the oh boy, I also need the angle between these two, don't I? I forgot about that. And so we need to do a little bit more work here before we compute that directly. So we need the sine of theta. Sine of theta equals what? Okay. Well, we can find the cosine of theta using the dot product formula. So the cosine of theta is U dot V over their norms. And so we have U dot V. Well, 3 times 3 is 9. And then plus -1 times -6 is 6. Plus 7 times 2 is 14. Divide by 7 square root of 59. This is a horrible number. 29 over 7 times the square root of 59. All right, so there's our cosine of theta. And if we draw an abstract triangle here, abstract right-angled triangle, and say, all right, here's our angle theta, then the cosine can be thought of as the adjacent side length over the hypotenuse side length. So if this is 29 and this is 7 square root of 59, then we can find this one as the square root of 29 squared minus 49 times 59. That's pretty bad. And I didn't think about how nasty this problem was going to be if we did it this way. But we can do that. And then the sine of theta is going to end up being the opposite side over the hypotenuse. So 29 squared minus 49 times 59 all over 7 square root of 59. And so if we multiply those two things together, we get that our area is equal to 1/2 the norm of U cross, or sorry, norm of U, norm V, and then times the sine of theta, which we just figured out was this, square root of 29 squared minus 49 times 59 all over 7 root 59. Oh wait, but this was the norm of V and this was the norm of U. I have them multiplied on here. So they actually cancel out. So this gives us another formula for the area, which is 1/2 square root of 29 squared. So 29 squared minus 49 times 59. Right, the 49 from. Yeah. So this is another formula for the area. And in general, here's what it looks like. Area of a triangle spanned by two vectors is 1/2 the square root of their dot product squared minus the squares of their norms. Okay, and that is a formula that you can use if you want. It can be more complicated, but that is one option. Okay, and now if we just go ahead and do the easier way that I should have done first, we would get that A is 1/2 norm of U cross V, which we computed up here, was 40, 15 minus 15. So norm of 40, 15 minus 15. And that is 1/2 of the square root of 1600 plus 225 plus 225. I just happen to know what the square of 15 is. Don't worry about why that was so quick. And this is then 450. So square root of 2050 divided by 2 should be our area, which hopefully, if you do this, is the same number. Okay. Moving on to our last problem of the video. We're given 3 vectors here, u, v, and w. And we're asked to show that these are coplanar. Well, okay, what do I do here? Now, to show that 3 vectors are coplanar, I didn't mention this in the last video, but you can use the scalar triple product. And let's think about what happens here. So 2 vectors are coplanar if the scalar triple product is equal to 0. And why is that? Well, if the scalar triple product is equal to 0, remember that the scalar triple product is the volume of this parallelepiped scaled or spanned by these 3 vectors, u, v, and w. If w is in the same plane as u and v, this parallelepiped has no height, and thus it has 0 volume. So we can compute the scalar triple product, and if it's 0, then we are done. So what do we have here? We've got u cross v and dot w. Oh, wait, but we also had a formula for this guy. If we go back, what was that formula? Put everything as a row in a matrix and compute the determinant. Let's go back over here, rewrite that. So I need u is row 1, v is row 2, and w is row 3. We've got 1, 4, minus 7, 2, minus 1, 4, and 0, minus 9, 18. And I want to compute that determinant. All right, here I'm going to show you a little bit of a nicer way to compute determinants. So if you see zeros anywhere, those are very, very helpful. So let's start with 1, 2, and 0. And the rule, remember, is 1, cross out the row and column, use this as your minor. So we've got 1 times the determinant of 4 minus 7 minus 9 and 18 is here, 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 and here. Oh, mistake, not 4 minus 7. Minus 1, 4, minus 9 and 18 for the 1 row and column. All right, and then subtract off 2 times the minor that I just wrote. So 2 times 4 minus 7 minus 9 and 18. Okay, and then plus the last minor, oh wait, but this coefficient is 0, and I multiply it by this minor, so that's going to be 0 no matter what. So plus 0, and I don't care what the determinant is because it's 0, or it's multiplied by 0. All right, now I compute these 2 by 2 determinants, and we get minus 18, subtract negative 9 times 4, so plus 36, minus 2 times, okay, 4 times 18, and 9 times 8. 4 times 18 is 9 times 8 is 72, minus 9 times 7 is 63. Okay, so this is positive 18, and this number right here is 9. So 18 minus 2 times 9 is 0. Awesome. So we got our scalar triple product being equal to 0, which means that the volume of the parallelepiped is 0, and thus that the vector W must be in the same plane as U and V. Okay, here's one little rule that can help you sometimes when you are computing determinants. Notice I have 9 and 18 here, and 18 has a factor of 9 in it. Let's rewrite this over here. We've got, is that minus 1, 4? Minus 1, 4, minus 9, 18. I want to compute this determinant. I can go ahead and factor out a minus 9, and I'm left with minus 1 times 4, positive 1 times minus 2. That is perfectly allowed. You can factor out a common factor from any row. You can also do it for any column as well. So I have 4 and 18 here. I've got 4 and minus 2 there. I can factor out a 2. So I have minus 9 times 2, determinant of minus 1, 1. 4 divided by 2 is 2. Negative 2 divided by 2 is negative 1. And now I get, let's see, minus 18. Minus 18 times minus 1 times minus 1 is 1. Subtract off 1 times 2 is 2. This is minus 18 times minus 1 is positive 18. All right, so this is a trick that you can use to make determinant calculation a little bit easier. If I were to come over to my first determinant, I could have factored out a 2 from here. I could not have factored out a 2 from here because I would have gotten 7 divided by 2 up there, which, okay, you can do that, but it doesn't make your work any easier. So you kind of have to just play around with determinants. After a while, you start to get a feel for it, and things get a little easier. All right, so those are all of our examples for section 1.4.